but any partial fraction decomposition problem. Start by factoring the denominator, because those factors in the denominator are going to make the denominators of your decomposition. So in our first example here, x plus 1 and x minus 2, we'll make those our denominators. Okay, and what's the next step in the process? What do we put upstairs in the numerators of these fractions? Yeah, we're going to put some a and b. And what do a and b stand for here? A and b are going to be constants. So let me ask at this point, there are some problems in which putting a constant upstairs is not enough, where we have to do something fancier like bx plus c or something like that. How do we know when we have to put something more fancy up in the numerator and how we can just get away with a constant some other times? Which, the power of which? Yeah, the exponent of which is going to tell you. Which exponents are we looking at here? Well, the numerators here. What is the degree? As a polynomial, what's the degree of these numerators? If I just write a constant up here, the degree is 0, because there's no powers of x. What's the degree downstairs of these denominators? 1. So what do we have to have in a good partial fraction decomposition? What has to be true about these degrees?
The numerator's degree is higher than the denominator's?
I would say other way around. We want the denominator's degree, the degree downstairs, to be bigger than the degree upstairs. So as long as that's the case, lower degree in the denominator than in the numerator, then we call that rational expression a proper rational expression. In the same way that a fraction like 6 over 11 is proper fraction, where a fraction like, 25 over 11 would be called improper.
Right.
When we're talking about fractions, not when we're talking about rational expressions. I totally got that backwards. Higher degree downstairs. Thank you. Yeah, that made no sense. So we want the higher degree to be in the denominator. And if the higher degree is in the denominator, we call that a proper rational expression. And those are going to be the kind that we need to know ultimately how to take the antiderivative of. And luckily, over the last couple of classes, when we talked about trigonometric substitutions, that was kind of our last step that we needed in order to figure out how to take the antiderivative of any proper rational expression of degree 1 in the denominator or degree 2 in the denominator. So as long as we can handle degree 1 and degree 2, there's a very deep theorem in abstract algebra that says that any polynomial that has degree higher than 2 can be factored into factors, over the real numbers anyway, with factors of at least degree 1 or 2, at most degree 1 or 2. So if we can handle the degree 1 downstairs case and the degree 2 downstairs case, then every other case can be reduced to one of those, one or more of those. Okay. So when we write down our denominators, we're just going to pick our numerators to have a lower degree. So if our denominators had degree 1, then we can use degree 0, i.e. constants, up in our numerators. All right. And I agree with what Daniel said, that this step, that if you slip on this step, in other words, if you don't give yourself enough flexibility with your numerators, or if you get the degrees screwed up or whatever, that the whole rest of this process is going to be very difficult. But as long as this step is good, where do we go next? Yeah, we have to solve for a and b, right? We need to know what the values of these constants are. And the requirement is that the sum of the two fractions on the right-hand side has to equal the fraction on the left-hand side. And so we're going to do what looks like a step backwards, right? We're going to take the fractions on the right-hand side and add them together, find a common denominator for them, and add the fractions. And what denominator can we use as a common denominator for both of the fractions on the right? X plus 1, x minus 2, which is exactly the denominator that we had in the beginning, which is actually a good thing. But when we get that common denominator on the right-hand side, where do our numerators come from? Right, the numerator of one times the denominator of the other. So my first term here is going to be a times x minus 2. And my second term in the numerator is going to be b times x plus 1. And then those are being added together to get the numerator of this recombined fraction. And then to finish our fraction, let's just simplify the numerator by getting rid of its parentheses and combining like terms. So we're going to have one term upstairs with an x in it. And what is the coefficient of x going to be upstairs here? We've got an a coming from the first term, and we also have bx from the second term. So I'm going to have a plus b here as the coefficient of x. And then we're going to have a constant, and that constant is going to come from this product and that product. So it's going to be negative 2a plus b. We're going to see how I did that. So now that we have this numerator simplified, now what do you want to do with it? Well, what is this whole thing supposed to have been equal to? Yeah, the whole thing is supposed to have been equal to our original fraction, and since the denominators are the same, that means that the numerators must be the same. And so we just have to require that a plus b, the quantity times x, plus negative 2a plus b, is equal for all values of x to the expression x. So how do we make that happen? How do we use this to figure out what a and b should satisfy? We've got to match up what's in front of our x on the left-hand side, and what's in front of our x on the left-hand side is a 1, right? The coefficient of x is 1. And then what do we match up negative 2a plus b with on the left-hand side? 0, because that's our secret constant term in the numerator on the left-hand side. And two polynomial expressions are equal for all values of x if and only if their coefficients are equal. And so we end up with a system of two linear equations. Negative 2a plus b is equal to 0 equates our constant terms. And our coefficients of x are equated by a plus b equals 1. And so we end up with a system of two linear equations and two unknowns, which we have techniques to solve. I'm teaching a linear algebra class that meets right after this one this summer. And this was our day 1 of linear algebra. We talk about this, solving a 2x2 linear system of equations in a variety of different ways. So what way would you like to choose to solve this linear system? What's convenient? Elimination? Substitution? Those are two biggies.
You could also just have as it is, plus, which is going to be like a negative a plus 2b equals 1.
And what does that do for us?
Absolutely.
Well, not absolutely nothing, but it's certainly, if our goal is to use elimination, in other words, to eliminate one of these variables, adding these two equations isn't going to eliminate a and it's not going to eliminate b, but what about subtracting? Do you have another?
System of equations?
Well, that's what this is.
Oh, sorry.
Right. This is a linear system of equations. So, depending on your comfort level with things like matrices and all that kind of stuff, you could make this into a matrix equation and apply elementary row operations to reduce it. But this class doesn't have that as a prerequisite, so we're just going to go with these as equations. And if I subtract the second equation from the first, I end up with 3a, but then my b's have canceled. And on the right-hand side, I get 1. Right, so we've eliminated b, and we can solve for a, and a is 1/3. And now that we know that a is 1/3, how do we find b? Just plug it back in to either equation you like. So if I put it back in for a in the first equation, then 1/3 plus b is equal to 1, so that b is equal to 2/3. Now, you guys are up on your fractions this morning. It's good stuff. There we go. So if a is 1/3 and b is 2/3, then when all is said and done, we can now go back and finish our partial fraction decomposition. So in place of a, in the numerator of the first fraction, we'll put 1/3, and in place of b, in the numerator of the second fraction, 2/3. And our partial fraction decomposition is complete. So in a partial fraction decomposition, we're not done until our denominators are what are called irreducible factors. In other words, we can't factor x plus 1 and we can't factor x minus 2 any further. Because if we could factor these denominators any further, we could do partial fraction decomposition again on those and break them apart into even more pieces. So we're done if all of our denominators are not factorable anymore. So starting with this example now, we would like, again, to perform a partial fraction decomposition that's going to get us the denominators x plus 1 and x minus 2 that we were looking for. But there's a bit of an immediate logistical problem with this. That if we tried the same form for our partial fraction decomposition, and then we simplify what we have on the right-hand side, we would end up with that same combination that we had before, a plus b, the quantity, times x, and then plus negative 2a plus b, and then that would be all over x plus 1 times x minus 2. But then, what's the problem? The problem is I would need to have a way of equating that numerator not with x, but with x squared. And that presents a serious problem. Because over here on the left, I have a term that has degree 2, right? I have an x squared term. But on the right, I don't have an x squared term. So I don't have any coefficients on the right-hand side that will let me make the coefficient of x squared in the expression on the right-hand side 1. So we can't do this. Even though this looks a lot similar to the example we just did. In fact, it's fundamentally different. So we have to do something else here before we even begin our partial fraction decomposition. Anyone remember from the readings what we have to do in an example like this? Because we're starting with a rational expression that is in fact not proper. Because the degree upstairs is 2 and the degree downstairs is 2. So what's our first move? So if we kind of think of our original rational expression as being like an improper fraction, then the process that we really want to do is to take this improper fraction and turn it into a mixed number. But how do you do that? How would I turn 31/5 into a mixed number? Divide 31 by 5. So like this. 5 goes into 31 6 times. Right, and so since my remainder is 1, that means that I can reduce this mixed number, this improper fraction, into the mixed number 5, which is the quotient of this division problem, plus the remainder divided by the denominator. 6, not 5. So we can get a proper fraction out of an improper fraction by finding what is the quotient. In other words, how many total times does the denominator go into the numerator? Whole times. And then our proper fraction is going to come from the remainder of this division problem. And it's exactly the same process for an improper rational expression like this one. So we're just going to do a division problem. Ironically enough, these division problems are simpler to do when the denominator is multiplied out instead of factored. So let's multiply out our denominator and then go from there. So get rid of this. Our denominator is, when multiplied out, x squared minus x minus 2. So that's our divisor, and our dividend is x squared. So here's our division problem that we have to do. And even though it's a division problem of polynomials, the algorithm is secretly still the same. We just have to ask ourselves, how many times does this go into that? How many times does x squared go into x squared? Once. And then in our algorithm, we'll multiply 1 by that divisor and get x squared minus x minus 2. And then just like in the division algorithm, we'll subtract that from what we had and end up with, downstairs, x plus 2. And so our quotient here is 1, and the remainder is x plus 2, which tells us what? How can I rewrite this improper rational expression in terms of its quotient and its remainder? So let's see. X plus 2 actually on the numerator up here, divided by, and then there's my denominator, x plus 1, x plus 2. So the point is that in doing this, we've now peeled off this quotient by itself, right? And it now just, we're done with that part, unless we then have to find an antiderivative for this. And what's left over is now a proper rational expression. And because it's a proper rational expression, we can go back to our usual method of partial fraction decomposition for it, with an a up here and a b up here. Question? Fix that typo. That is an x minus 2 in the denominator. All right. So long division is your first step if you're starting out with something that is improper. And from here, now we just have to find the partial fraction decomposition for the proper rational expression, x plus 2 over x plus 1, x minus 2. And glossing over the details because we already did those details, we would now have a plus b, the coefficient of x, still equal to 1. This 1 over here on the left-hand side. And then negative 2a plus b, the constant term, would now be equal to 2. That 1 and that 2 coming from the coefficients in that numerator. All the details in getting to that system of equations are identical to what we did before. And then the solution of this. I will let you check this on your own, but a equals negative 1/3 this time, and b equals 4/3. So if you're hungry for those details again, feel free to watch the video of the first phase of this presentation after class is over. Again, same steps. The last thing that we haven't talked about is what happens when we have a rational expression in the denominator that is irreducible. Let's say I have x times x squared plus 1. And then maybe a 1 upstairs. So I can't factor this denominator any more than it's already been factored. So what are the denominators in my partial fraction decomposition going to be? X on the one hand, and x squared plus 1 on the other. And if those are my denominators, then what's my numerators? What should my numerator on x be? Yeah, there we can get away with just a constant, right? Because the denominator is degree 1, so we just need the numerator to be degree 0. But what about over x squared plus 1? There we go. Because we have to have enough flexibility to have the most general proper fraction that we can possibly have over there. And if the denominator now has degree 2, then we should choose a numerator that has degree 1. After this, though, the rest of the process is still the same. Recombine the denominators. And I'm not going to dwell on this example because I don't want to take up too much of your time. But There's our denominator again, and then we'll have the cross products in our numerator. So a times x squared plus 1 plus bx plus c, the quantity, times x. And then when we combine all of those terms in the numerator, we're going to have as our coefficient of x squared, well, one of our x squareds is going to come from the a times x squared. The other x squared is going to come from bx times x. So I'm going to have a total of a plus b of those. The linear term x, we're going to get, the only linear term x is going to come from c times x over here, so we'll just have that. And then our only constant term comes from a times 1. And so all told, we just need that whole thing to add up to 1. Reading across the numerators. So what is our system of equations this time? Or maybe I should say it this way. What is the coefficient of x squared on the left-hand side? 0. There are no x squareds on the left-hand side. What's the coefficient of x on the left-hand side? Also 0. We don't have any x's by themselves on the left-hand side. And then the constant term is 1. So our system of equations begins with a plus b, the coefficient of x squared, is equal to 0, and continues with the coefficient of x is also 0, and finishes with the constant term equals 1. So now we have a 3 by 3 system of linear equations. Luckily, though, this one is much simpler to solve than most. In fact, the third equation already tells us what a should be, and the second equation already tells us what c should be. So with that information, what is b? -1. Yep. So b is equal to -1. And we're done with our partial fraction decomposition. So we would just go back to our general form here. And in place of a, I'm going to put a 1. So we'll have 1 over x as our first term. And in place of bx plus c, we're going to have -1x plus 0. So in other words, minus x is going to be our second numerator. And just because I have to ask a calculus question, how would we find the antiderivative if we were finding the antiderivative of 1 over x? What would that become? ln of absolute value of x. And how would we find the antiderivative of x over x squared plus 1, the second piece? Say again? What technique do we need from this semester in order to find that antiderivative? U substitution. What's a good U substitution? X squared plus 1. Okay. Because then du is equal to 2x times dx, and that can account for the x in the numerator. And this antiderivative ends up being, well, what does it end up being? Minus the natural log, minus 1/2 times the natural log of x squared plus 1. That I'll let you check on your own. So we can find the antiderivative only after we've completed the partial fraction decomposition. And once we have, then a combination of natural logs, substitutions that become natural logs, or the very worst case scenario is you might have to use a trig substitution if this expression on the right turned out not to have an x upstairs. If it were just 1 over x squared plus 1, then you would be stuck with a trig substitution. But all the techniques we have in our pocket at this point are then sufficient to finish a partial fraction decomposition integral.